First of all, I think it's sensible to say kudos to organizers. It's so cool to see everyone here and slowly building this network of professionals who are working here in Prague and nearby cities. Really, thank you. Thank you guys for organizing this. It's super cool. These days makes understand that we are doing work together. That's cool. So today I will try to share one of the research that is more of a independent investigation other than affiliated with one of those companies. You see, I'm working as a security researcher at Microsoft, but this is more of a independent research, how we can foster techniques that empower GPT-like systems for our own domain. And a brief bio here, just because the psychological studies show that if you trust my authority in this question, you will remember material better. So basically more than 10 years of experience in both blue team and red teams. I actually did a red teaming for several years. Now switched back to do AI-powered detection engineering. And 2 master degrees, one on network security, second on data science, and the PhD, which is ongoing in Italian universities. Bunch of certificates and presentations in different venues. So there is some experience in this domain, and we can start. I don't want to overburden you with some low-level details like demos from terminals or something. I want you to enjoy the talk and came out of here knowing something new. And this new, we will go over the concepts that power this kind of multidisciplinary research from various directions, and you will get intuitive understanding after this talk. So we'll start with the threat model, which is actually defining the problem we are trying to solve. Then I will show what is dynamic malware analysis for those who are not familiar with this concept a lot. Then we will touch on AI topics, basically self-supervised learnings and transformer neural networks. So you will get to know what it is. And then basically I'll touch the experiments that we did in this research, how it works, and some ideas on a future work. So if you are interested in this, feel free to reach me out after. We can, maybe work together for future ideas. So threat model. Speaking about malware detection, a lot of times the discussion comes only about PE files, right? Exe and DLLs, how we detect suspicious stuff in this executable and that executable. But actually, code threat perimeter is much wider. And this is only one operating system. If you think on others, there's different formats, different ways to execute stuff. And moreover, there are techniques that use legitimate software to do malicious stuff, like living off the land. So there should be a common denominator over all of these things, and those are system logs. Basically, it's a behavior of a system, like a human. We can take a look how human behaves and infer his intentions. The same is happening when we take a look on system logs. That's why a huge kind of set of industry professionals work in this space. When we speak about the raw formats, it's only like incident response and digital forensics and the AV vendors. 90+% of people work in system log space in conventional SOC operation centers, security operations centers. So this stuff is fed into the seams where detection engineering happens, and then you get these alerts to the security analysts. And for those who are not that familiar with system logs, what they consist of, it's machine language, right? On the contrary to the natural language, which is like English, French, Czech, we have machine language, which is kind of ubiquitous among the different formats. You have key value pairs most of the time, short kind of machine strings that are arbitrary between different maybe fields, like API hash can be completely random, file path is less random, but still can have a different values. And oftentimes it has a timestamp, so we can infer this information to build an AI solution on top of that. There are challenges in system log space, and to solve them, you actually need a M6 box. It's horrible. It's hard to acquire supervised data sets in system log space. It's even, for those who don't know what is supervised data, it's actually when you take a human and he labels data, and this label goes into the AI model as a knowledge. And here, it's hard to know what to label, single log entry or or maybe all data from compromised system? If yes, then within what time period? And if we answer those questions, it's expensive. You have to, your time should be spent on that. And we don't want to spend human hours to label those entries. And because there's a huge amount of them, like enterprise businesses have terabytes of logs per day and many more problems. It's like untractable with a human resource. That's why we can use a dynamic malware detection as a proxy task. What I mean by that is with the dynamic malware analysis 101, you take a PE file, you pass it through the sandbox or emulator, and you basically get a representation of what happens in a system. Like process chains, command lines, what API calls it does, like what operation it performs in registry, in network, in file system. And passing thousands of samples through sandbox, it's kind of hard for deep learning quantities. They require huge data sets. For this research, I used an emulator, which is basically a replica of operating system. And luckily, Mandiant supports one of the emulators, Speakeasy, focused solely on malware tasks. It's basically in 4 lines of code. You can get a behavioral representation of what malware does on a Windows system. Emulators are not perfect. It's kind of software engineered replica of real system. So there are errors across different malware families, but it's still tractable. Like 95, maybe more %, it still expresses some behavior in emulator. And we can improve this stuff. For example, like what we did, like we contributed to the Mandiant solution when I researched this with some extra functionality that was in the malware datasets that I've seen and is not yet in the Speakeasy. So how look those emulation reports? Network that malware called the registry access, file access, like file that is dropped on a system and even its contents is there. API calls. So this really resembles how actual system logs look like. So we can apply AI logic on this, and if it works well on this data, we presumably can transfer it to the real system logs. And the process might look like this. I will cover what is self-supervised learning in a moment, but basically we can investigate. We want to achieve a good self-supervised learning for detection logs, for detection on system logs. But there are no benchmark data sets, and the data is sensitive. That's why we don't have those public data sets. If I take system logs from your organization, it will contain stuff that you don't want to be public, right? And that's why we can consider a malware detection as a proxy task. There are data sets, there are rich literature, there are lots of research on this domain. And we can evaluate relative performance of the methods, like self-supervised learning algorithms, and then transfer those algorithms to the actual system log analysis. What are those methods that we want to explore? So self-supervised learning and transformer neural networks. Let's start with the neural networks. It's basically deep learning is a branch of machine learning that builds and ends neural networks. In the second decade of 21st century, convolutional and recurrent NNs ruled the world. First introduced by, at the end of the 20th century, LeCun introduced convolutions. It's a basically method to infer patterns from a two-dimensional structure like images, but it can be applied to one-dimensional structure as well, like sequence of strings. And then in 1997, LSTM, which is one of the most common manifestations of recurrent neural networks, was introduced, which is basically passing the same data through the same neuron again and again. And these methods ruled the world in second decade of 21st century. But everything changed when Google released the called Attention is All You Need paper, which kind of releases and introduces the transformer model. And maybe you've seen this image, maybe not. That's what kind of rules the world now and powers the LLMs and basically any other success in AI today. For example, in GPT, T stands for transformer, generative pre-trained transformer. And what transformer uses, it has this attention mechanism inside, which is distinct to the recurrence or convolutions. It has this weighted average over the tokens within a layer, and first used for machine translation, but then kind of ubiquitously used in all the fields. If we see, for instance, state-of-the-art solutions in 2016, each domain had its own kind of fine-tuned solution, and like computer vision engineers didn't work in NLP domain and vice versa. But today, basically, Transformer overtook all those domains and kind of, is the best architecture for any of those tasks. And since then, there are no really kind of clever breakthroughs. It's just scaling up and kind of good engineering of the existing technique. And the models keep growing, and surprisingly, they give a better results. And that is kind of indeed surprising for even experts in the industry. What is main contribution, for example, of OpenAI is that they were the first ones who said, why we don't try to spend millions on this and see what comes out? Because before that, like, people thought that they need something else, and they kind of thought, okay, let's run this thing for longer than others, and something appeared, something emerged, and systems become better and better. Why is that so? Like, the main reason is that Transformer scales up really well. It is efficient architecture that parallelizes super well. But the idea behind this parallelization is self-supervised learning. You cannot scale up really to huge quantities with the supervised data. You don't have enough humans to label everything. But GPT is trained on the whole internet, right? So how they do it? Through self-supervised learning, SSL. I will use this abbreviation, although it's overloaded in our domain, right? HTTPS, thank you. But so how SSL works? You have this huge unlabeled corpus, like wiki, Reddit, books, whole internet. You do this pre-training using SSL methods, and that's where 95+% of compute comes in. That's where the majority of the work is done, is this pre-training. However, then the model, this produces so-called foundational language model that should be fine-tuned in a way. And you can do this with a smaller but labeled data and to do specific tasks, like ChatGPT solution does question answering, basically instruction following, but you have other kind of things like malware detection. And you have fine-tuned many models out of the same foundational model, which is cool. How these techniques work on natural languages, basically, which is textual data as well. There are two competing methodologies. One is the GPT-like, more scientifically called autoregressive, but it's dumb as F. It just predicts the next token. That's it. So you give it a context and you try to predict what's next, like nothing, next word is, and nothing is, and model should predict the word impossible if this is in data. The another idea is masked language modeling for BERT-like systems. And basically it takes the whole sequence and corrupts it. It hides specific tokens inside, and then model should predict what is hidden. Like in this case, instead of mask, it should output brown. And those two competing methodologies worked alongside in 2017, 19, but then looks like the GPT-like autoregressive is more efficient over the time. But in our case, I tested both of them. We will see the results. And one interesting notion for our domain is that maybe we don't need those huge quantities of compute, because that's cool, but we cannot train this, right? We need data centers like OpenAI has. Actually, no, there is evidence in some people who are kind of really experienced in the domain, like founder of the Hugging Face of Orly Kuhn that was mentioned earlier, who's like head of Meta AI right now. They think that in narrow domains we actually may come to use small language models, and that might be a case for us as well, because large language models are good when people interact with them, but when you have to make thousands of queries, 10 of thousands of queries within a day, this model is not tractable. So you have to make, for machine-to-machine communications, where we want to build detections, for example, we have to build more computationally sensible models here. So when we speak about how we can use this knowledge to approach our domain. So this is the model that I used for the malware detection. Here we have this first step of the kind of extraction of behavior from something, either its operating system or the like P sample. Then you have a data cleaning step, which is, I'd say, super crucial for our domain, and that's where the domain knowledge can come in. That's where you guys are really relevant for those data science projects, because when you take a like vanilla data scientist out of the domain, sit him next to the computer and say, solve me cybersecurity problem, they really like cannot do this. Unlike like natural language domain or computer vision, it's like more intuitive. Here, people have a really huge entry curve, and they are lost in those steps like data cleaning. What I mean by this, for example, filters. You have this blob of machine data, right? And you can take it as this and pass it into the model, but like take a look on the unique tokens. Tokens, we will touch a moment what it is. It's basically a unique unit that model uses. When you don't filter anything, just take raw JSON, it produces huge amount of unique elements that model has to understand. But when you apply some filtering, for example, you take API calls, actually it's not only names, it's the arguments as well to the API calls. It produces more tractable size of the stuff, and model can already operate more efficiently in the space. And this is logarithmic scale, it's not half, it's like, yeah, it's like exponentially lower amount of unique tokens here that model have to understand. And that's because there are non-essential values like memory regions. Basically, memory regions rarely, if only, say something about the malicious or benign behavior in emulator, at least. There are hashes which are completely arbitrary, and the exact values in hash do not matter at all. And if you do not apply any filters, this is the ROC curves, and yeah, it's not fancy, it's not kind of exploit or something, but you have to infer to this type of evaluation of your work when you're working in such quantities. And basically, ROC curve, the higher it is, the better it is. It's like kind of higher detection rate under the same false positive rate. If we don't apply any filters, it's so bad. It's like, first of all, it fluctuates a lot depending on the initialization, and then it's just plain bad if compared to the clever domain knowledge influenced filter. What I did here, basically, for the field experts, it's obvious. We filter for file access, for network events, for registry access and APIs, and everything else goes away. And this is the best setup according to my tests. And yeah, another thing to do here is normalization. We can and want to replace some of the stuff in original data with the so-called placeholders, for example. And the model, instead of going like digit by digit, character by character in the hash, it can grab the information that this is just a hash there and learn a token depending on just that. And this increases efficiency of such models significantly. The same applies to the IP addresses and many other fields. And this is like never-ending loop where the domain knowledge can come into such models. So if you participate in any AI-related projects on your organization, this is the field where you can kind of flourish. So then what happens next? Then goes feature extraction step. This is more of a like native AI already direction where the kind of data scientists have the credibility. Basically, again, tokenization. So what is a token? It's a unique element, like an atom in a real world that you cannot split further. Yeah, you can kind of talk about quarks, but like they do not live independently. And here the tokens, that's the unique element. So the string can be split into the kind of, yeah, tokens here. Here it's like plain and dump based on words, but like for intuitive understanding, it's enough. Then you get a token and you encode it with a vocabulary, which basically corresponds with a specific integer behind that. And the vocabularies are fixed. GPT-like systems, for example, GPT-2 used like 50,000 tokens. Modern, like GPT-4, we don't know, but kind of 3.5 uses around like 100 tokens. 100,000 tokens, sorry. And then you go and expand this token into like multi-dimensional embedding space. And embedding is kind of hard to grasp, but you can think about this. It's like those vectors into this multi-dimensional space kind of group together based on like semantic similarity, on the meaning. For example, similar API calls will be close together in this like multi-dimensional space. Like, I don't know, get file A and get file V will be super close there, even though they can be represented by different tokens. So yeah, what we do here, we take this record, the JSON file, and we go like token by token and flatten it. We discard some of the stuff that we don't want, like keys. We don't want it to replicate them all the time. And yeah, in this work, I used both white space tokens and BPE tokens. BPE is the stuff that actually GPT uses. It's more a data-based tokenization with co-occurrence of data in like data set. If it sees that those two characters appear often, it will create a token for this. And it does this like incrementally over time until it reaches the vocabulary size. So yeah, and then that's it. Basically, you have this vectored representation of data. You pass it to the model, which is just transformer in this case with little to no modifications. So what we do with the experiments, I collected a data set, about 95,000 of samples across two training set and test set. You do not train on test set, you evaluate your performance there. Several malware families, cleanware, and how you do it actually. You have this training data, 70,000 of samples, test data, 25,000 of samples. You choose large part of training data set to act as an unsupervised corpus. You take this blob, in this case I took 80%, and just discarded the labels. Assume we don't know labels for this part. Then we pre-train a model using those both techniques and without any labels at all. So basically for MLM, you mask them, pass through the transformer and ask which tokens are masked. For the GPT-like, you pass a context and basically ask which token comes next. And then you have this foundational model, let's call it that way, and you fine-tune it on a small part of supervised data, labeled data, where actually humans, let's assume, labeled it. And you evaluate how it performs on test data compared with different scenarios. So this is the results. The blue one is kind of the perfect model. Let's say it knows all the labels in the training data. We can use it as a like upper bound model that has all the knowledge of the labels in the data. Then we have this lower bound model that uses only 20% of the data and the knowledge there. And we have this fine-tuned models. In our case, it's green and yellow, which is basically green is GPT-like, yellow is this masking pre-training. And we see that it indeed is somewhere in between, with MLM actually doing worse on the lowest false positive rates than this lower bound model, meaning that it kind of pushes away the model farther than actually just fine-tuning it. But the most surprising part is that with the autoregressive GPT-like pre-training, you almost match the performance on this best model that knows everything out of the data with only 20% of the labels. You can put it that way. Here you have like 10 reverse engineers sitting and labeling really this like large data set, and you get a model, right, with all the labels. And here you have the self-supervised pre-training on most of the data and just 2 engineers labeling like small portion of data. In this case, it was 20%, and getting the same results, basically. So I believe that's cool. And again, this is kind of dirty preliminary results without huge data sets, without huge computational resources, but this kind of hints us into the correct direction already. So this might be interesting stuff to explore, throw more compute on. Yeah, one interesting thing that came out of this, especially for domain experts, is this explainability part of those models. So I just took a random sample without any cherry picking or something, and just took a look what activations are there in the transformer. And you can see that some tokens are more kind of emphasized by model to correspond to maliciousness. For example, in this sample, it was like exaDOS token and get tcount token. And get tcount actually is used in some of the handcrafted rules for anti-debugging, right? It's like timing-based anti-debugging. And the malware uses it to determine whether to execute further logic or not. And exaDOS is basically oxymoron from like two components that are common in Windows, but are actually, this string is never seen in a default Windows system. There are no exaDOS like in a file path anywhere. Yeah, so that's cool. This might be used as an like focal point for reverse engineers that can use this to kind of narrow down their scope of analysis of a sample to build later manual, more robust rules or something. And I checked this with the more sensible, explainable AI techniques, and they correspond. Like you can use many techniques and they kind of match each other, and so you can use more robust ways to get this knowledge out of the model. So yeah, some of the ideas on future work. I'd say this stuff, the GPT-like pre-training, is not the best for this type of data, right? In natural languages, when I say a word, it's easy to predict what comes next, right? And in the system logs, it's harder because, yeah, values can be arbitrary. The IP address can be like different. The file path can change independently on the context. So I think we can influence here from other domains or come up with something new. For example, in computer vision, those models that you've seen, like Sora from OpenAI recently that creates videos, or like Midjourney, if you heard, they don't use this type of pre-training. There's different ideas, mostly based on diffusion and augmentation. For example, this BYOL, bring your own latent pre-training, takes basically an image and augments it in two ways. Like it crops it, and I don't know, in this example, it rotates it. In other case, it makes it darker. And it kind of tasks a model to kind of predict that those two examples are still the same. Make the difference between them as low as possible. And in the other case, you can take completely different image and make the distance between them like as far as possible. And that way, model interestingly learns a lot of concepts about the input data as well. So we can use some mix of ideas here, build maybe custom pre-training for system logs, for malware data, and yield even better results, surpass the labeled data. And yeah, ideas are, I'd say, limitless here. And about reproducibility of this work, you can take it, it's public, the data public, the code is public, installable with pip. If you want to play with it, feel free. And yeah, even the technical report in form of paper is published on Arxiv, so feel free to grab it. Yeah, and that's it for this talk. If you have any questions, I don't know, do we have a question sessions here? Probably not. Yeah. And yeah, if you are interested to chat, grab me any moment today. We can discuss these ideas. Don't hesitate to come close. Cool. So if no questions, yeah, we can.
Is there any question?
Hey, so you said that the logs are unlabeled, and therefore you need, for example, GPT, but aren't they structured in the way, for example, of JSON, where they have predefined keys or different forms? The question is, why to use GPT for natural language when you can make, for example, XGBoost, for example?
XGBoost, you mean? Yeah, why we use, okay, can I paraphrase the question? So we have this system logs in well-defined structure, and if I understood correctly, why do we use GPT-like systems, like ideas that are tuned for natural language, if we can use XGBoost? For example, yeah, XGBoost is a tabular model. It's not a deep learning solution. It's like a different machine learning algorithm, which is kind of does the same, but it's a purely supervised model. You cannot really apply those self-supervised pre-training ideas on XGBT solutions. But you're right, for many tasks where you have a well-defined supervised model or a supervised data set, you can use GPT boost, which is like gradient boosting, much better than the deep learning solutions. And that's one of the things, in practical applications, it's not sensible to go like neural networks right away if you have well-defined data. Use some more like easy algorithms here. But yeah, for this example, if we want to pre-train, we have to go to the neural networks. XGB boost cannot really parse these self-supervised learning algorithms into it. It doesn't work. We have to have attention here. I hope it answers. Yeah, maybe I would hear it that way.
Thank you very much for the great presentation. Just a following question to this one, is that the data you use is somehow a structured data. So why do you use this kind of language, LLM-based or a small language-based data? Because they are not unstructured data. So what is the reason? Yeah,
probably you are asking between dichotomy with so-called feature engineering that you can do on top of the structured data. So you can predefine rules that can extract something out of it, and we actually, there are good solutions, and I'd say the best solution so far for malware detection, static malware detection, when you take a PE file and don't execute it, but just take it as a raw byte blob, is based on the feature extraction from it, because it's like structured data. It's like RFC standard, right? And it's called Ember, and you extract a feature vector out of it, like static one, and you apply, and it works really well. But it has some limitations. And one of the limitations, again, it's purely supervised. You have to label all the data, and especially for system logs, again, it's not tractable. So if you want to extract some feature vector from system log, you have to define it. Yeah, what it is. And the idea behind those self-supervised learning algorithms is that you make as little as possible manipulations to the original data and let the deep learning extract itself the kind of valuable representations out of it. So I'd say both, again, solutions are viable, but the feature engineering approach historically proven to be good, but not scalable. And like back in 2000, I'd say 5, in computer vision domain, they used as well feature extraction techniques, like they extracted edges or something and built like feature vector out of the image. And it kind of worked, but as we've seen, if you build a convolutional network that extracts itself the cool feature out of data, it's just better, and even more with this self-supervised learning. So it's kind of a next step that we can influence from other domains in our domain. But actually, yeah, in our domain, we are still backwards, and the good solutions use feature extraction. But yeah, maybe we can come up with something better here.
Any other question?
Thanks. Very simple question. I'm not sure I get the whole message here, but if you have a language model like this, you feed it with a prompt or kind of it. So I suppose you feed it with a set of tokens or whatever you extract. So what's the outcome? It tends to finish the sequence, right? So what would do it in your case?
Yeah. Again, it's again difference between so-called generative applications, right? You can fine-tune this large model to do different tasks later, right? One of them is actually instruction following. You give it the context and it predicts output, like ChatGPT, right? You ask it and it answers back. But you can tune the model, do something different. And in this case, what we do is basically you pre-train model and then you do a different fine-tuning. You say, I pass a sample through a model, but I don't want you to follow what comes next for this case. You just give me a representation, what you think about it, and let's classify it, whether it's bad or good. So with this fine tuning, you can play it with the model, and you can, like with the Lego pieces, you can build a different solution for different application. You can think of it, you can ask a ChatGPT something, it will output, and if you have a word true, then it's 1, and if the word false, then it's 0. But it's like naive way. There are more low-level way where you can just take a vector, so-called numbers out of the model and steer into direction, whether it's good or bad. Yeah, I hope it answers your question.
Yeah, kind of.
Yeah. It's already engineering of neural networks, and you have to make more informational steps, like knowledge gap should be covered to kind of understand this. Yeah. It's basically a bit out of scope.
So you turn this language model into a classifier.
Yeah. You can say it that way. Yeah, like based with some engineering tricks. Yeah.
Thanks.
Any other?
Yeah. Okay.
That's it.
Yeah. Thank you everyone for attending.